Okay, so now let's see how we can show that. Let's see how we can show basically these two things over here, 1 and 2. So in order to show that, what I'm going to do is that, again we get into the problem of space, and what I'm going to do is that I'm going to open another. I am going to open probably another window here. Let me see. Okay, so now I ended up actually opening another window because actually there was no other way of doing it. So first we wanted to show that basically GOF inverse composed with GOF is equal to I of A. That's what we wanted to show. So now let's see how we can show that is the case. Okay, so that is basically GOF inverse of GOF. So let me see the argument of f is basically f is a function from a to b, and the arguments can be basically 1, 2, or 3, right? So I can write this as basically GOF inverse. This is basically one function, and that is one function of g of f of x, right? That is g of f of well, we have no x here, but the inputs to f would be 1, 2, and 3. So let's try, for example, 1. If I tried 1, I would get, now f of 1, as you know, is equal to a. Now, of course, it's on the other monitor, I can see it, but you cannot see it. I'll put it over here if you need to. You can make a screenshot here, and then whenever we talk about it, you can just simply you can make a screenshot here. You can basically pause this video, make a screenshot, and so that you can have access to this page, right? So now g of f of 1, as I can see here, is equal to a. So that is the same thing as GOF inverse of f of 1 is equal to a, so that is g of a. And g of a is basically apple. G of a in the function g is defined as apple. So I can write this as GOF inverse of apple. Now GOF inverse of apple is equal to 1. This is equal to 1, which means that GOF inverse of GOF inverse composed with, basically you can write this even as, I mean, to begin with, you can this statement, you can, or this expression, you can write it as GOF inverse of GOF, or composed with GOF of 1. And then you can write it this way, right? And then you will get to 1. That means that if you write GOF inverse of GOF inverse composed with GOF of 1, that gives you 1. Now on the other hand, if you write GOF inverse of GOF composed with GOF of, and another input that you can try with F is 2, for example, which is the same thing as GOF inverse composed with GOF. Now this you can write as basically GOF of 2. This you can write as basically G of F of 2, basically. G of F of 2. Right? So now F of 2 is equal to B. F of 2 is equal to B. And so I can write GOF inverse of basically G of 2. Now G of 2 is equal to I'm sorry, this is supposed to be equal to B actually. G of 2 is equal to B. So G of B is equal to ball, right? So I can write this as GOF inverse of G of B is equal to ball. Now GOF inverse of ball is defined as 2, right? So that means that basically, and if you try the third input for F, what you will get is that GOF inverse composed with GOF of 3, that will give you a 3, right? So that means that the function that means that basically means that the function, basically this function over here, GOF inverse OGOF, that means that GOF inverse OGOF, that is the identity function on these on the set that contains these values 1, 2, and 3. And that is basically the function A as we had before, because basically the set A was basically 1, 2, and 3, and this set A is actually the domain of GOF as well. Is the domain of GOF as well. Okay. So that is basically the first part that we wanted to show. We wanted to show that GOF inverse composed with GOF is equal to the identity function on the set A, which is the domain of GOF. Now we need to show that. We also need to show that basically GOF composed with GOF inverse is equal to the identity function on the set C. And here basically, to give you some explanation, the set C is basically the codomain. Is basically the codomain of GOF, which is basically apple, ball, and cat. Apple, ball, and cat. That is basically the set C. So now how do we show that? So we have GOF composed with GOF of basically GOF inverse of basically the input here is equal to I of C. Now, I need to input the values that can be input into GOF inverse. So I write this as GOF of basically this function GOF inverse, and I put this O over here as well for now. And the possible inputs to GOF inverse are basically apple, ball, and cat. So I try, for example, apple. I try apple, for example. That gives me basically GOF of GOF inverse of basically apple. Now GOF inverse of apple is simply 1. This is simply equal to 1. So that is GOF of 1. Now that is the same thing as GOF, that is G of f of 1. G of f of 1. Now f of 1 is equal to, and I'm assuming that you have access to the page that we were writing before this page, so you can follow me on everything that I'm writing here. Now f of 1 is equal to a, so that is G of a. And G of a is equal to apple. So as you can see, GOF, as you can see, GOF O GOF inverse of apple is equal to apple. And if you try other values of other inputs of GOF inverse, what you will get is that basically GOF O GOF inverse of, for example, ball, is equal to ball. And also what you will get is that GOF of GOF inverse of, for example, cat is equal to cat, which means that this function over here, GOF, composed with GOF inverse, is the identity function on the set that contains these elements, because you are inputting these elements into this function and you're getting the same things basically: apple, apple, ball, ball, and cat, cat. Now this set that contains these elements is basically C, right? And to give you some explanation, C happens to be C, which is equal to basically apple, ball, and cat. Apple, ball, and cat is the codomain of GOF. Is the codomain of GOF, right? Is the codomain of GOF. Now, what we showed here was that basically GOF inverse composed with GOF is equal to I of A, and the identity function on A, and A was the domain of GOF. What we showed here was that GOF composed with GOF inverse is equal to the identity function on C, and C is the codomain of GOF, right? Which means that basically GOF inverse is actually the inverse of GOF, which means that GOF inverse is the inverse of is the inverse of GOF, and that GOF is invertible. Right? So that's what it means. And this is all based on the fact that we said that basically if you have, for example, two functions, suppose that you have a function f that goes, for example, from set A to set B, and you have some function g that goes from set B to A. If I want to show that g is the inverse of f, to show that g is the inverse of f, we need to show that basically GOF is the identity function on the set A, which is the domain of f, and also FOG is the identity function on the set B, which is the codomain of f. So based on this, so now you can use this in any context that you need to. Meaning that now over here in this example, it got a little bit more complicated because I had some function, because I had some set A over here and some set B over here and some set C over here and some set C over here. We had some function f over here, we had some function g over here, and so of course based on these two functions you will get some function GOF, right? So then if you want, now what we wanted to do here, we wanted to show that GOF is invertible. So what we did was that we wanted to show that GOF is invertible. What we did, we defined some function GOF inverse, and we assumed that was basically the inverse of GOF, right? Now again, based on the logic that we used here, we said that if you want to show that G is the inverse of f, I need to show that GOF is equal to I of A, right? So then in order to show that GOF inverse is the inverse of GOF, I need to show that one, basically GOF inverse, meaning the function which is supposed to be the inverse, composed with the original function which is GOF, is supposed to be the identity function on the domain of GOF, which is A. That was the first thing that we showed. And second, you see I have GOF here, FOG here, meaning that you have to basically change the order of these two functions. So instead of GOF inverse, I write GOF composed with GOF inverse. That is supposed to be the identity function on the codomain of GOF, which is C. That was the second thing that we showed, and that's basically what you need to show in order to prove that basically GOF inverse is the inverse of GOF. So that was basically this part. Now the next thing that we need to show here is that so basically let's get back to the question that we had. So we started here. we had our function f here, we had our function g here, and these were the rules of the way that the functions were basically defined. And we wanted to show that fg and gof are invertible. So we already did this. And we wanted to find out f inverse, g inverse, and gof whole inverse, which we already did. So we found these three as well in the same process. And basically what we need to do now is that we want to show that gof inverse is equal to f inverse composed with g inverse, which is something important that leads us to a theorem in after this exercise. So that's what we need to show as well. Okay, so the next thing that we want to show here is that basically gof inverse is the same thing as f inverse composed with g inverse, right? And I think we can use the information that we have here. Of course, you have hopefully take a screenshot here. And now we can work with that. So we want to show that GOF inverse is the same thing as F inverse composed with G inverse. So now GOF inverse is basically the function that we defined, and we basically showed that GOF inverse was actually the inverse of GOF. So we showed that GOF inverse is the inverse of GOF. And the arguments that GOF inverse accepts are apple, ball, and cat, meaning that GOF inverse of apple is equal to 1, and GOF inverse of ball is equal to 2, and GOF inverse of cat is equal to 3, right? So now let's find out what is F inverse composed with G inverse. Now F inverse composed with G inverse. Now G inverse basically accepts these basically G. Let's write down these over here. G is a function that goes from B to C, right? G was a function that goes from B to C. That means that G inverse is a function that goes from C to B. And what that means is that then G inverse of basically apple is equal to A. Apple is equal to A, and G inverse of basically ball is equal to B, and G inverse of cat is equal to C. So I can write basically F inverse composed with G inverse. I can write it as for example, I can try each of these different arguments of G inverse and write it as F inverse composed with G inverse of, for example, apple, right? And then I can write it as, for example, F inverse of of G inverse of apple, and then I can write G inverse of apple, as you can see, is equal to A. That means that it's F inverse of A. Now F inverse of A is equal to 1. F inverse of A is equal to 1. And so let me basically separate these. So which means that basically F inverse composed with G inverse of apple is equal to 1. And as you can see, GOF inverse of apple is equal to 1, and F inverse composed with G inverse of apple is equal to 1. Now by the same process and logic, you can say that F inverse composed with G inverse of, for example, ball is the same thing as I don't know what happened to my eye. Is the same thing as basically F inverse is the same thing as F inverse of G inverse of ball. And that is equal to G inverse of ball is equal to B. So that is F inverse of B. Now F inverse of B is equal to 2. That is equal to 2. Which means that F inverse composed with G inverse of ball is equal to 2. And as you can see, GOF inverse of ball is equal to 2 as well, right? So we have tested 1 and 2, and also F inverse composed with G inverse of, for example, cat is equal to F inverse of G inverse of cat, and G inverse of cat is equal to C. So that is F inverse of C. Now F inverse of C is equal to 3, which means that F inverse composed with G inverse of cat is simply equal to 3, which is the same thing as GOF inverse of cat, right? So now based on this, you can say that, of course this is no proof, but then you can say that GOF whole inverse, you can say that basically GOF whole inverse is the same thing as F inverse. And as you can see, basically you have to change the order of them. F inverse composed with G inverse. That is basically what we wanted to show, right? So that was question number 27, which basically leads us to a theorem. Now the theorem here is, let me get some more space here. There, 100, 190. Which leads us to the theorem that theorem number 2. So if you basically, we need the theorem number 1 as well, and I suppose you might have forgotten that, so I repeat theorem number 1 here. In theorem number 1, we said that if f is a function from x to y, and g is a function from y to z, and h is a function from z to s, if these are functions, then we can say that h composed with basically g composed with f is the same thing as h composed with g whole composed with f. That was theorem number 1 that we also proved, right? Now, the example that we did in number 27 led us to theorem number 2, whose basically proof is based on theorem number 1. That's why I repeated this over here. So theorem number 2 is basically as follows. So you have let f, a function from x to y, and g be a function from y to z, So let these be two invertible functions, and as you saw in the previous example, what we had was that you saw over here that basically the function f was from basically this set 1, 2, 3 to ABC, and it was a bijective function. Also, the function g, you can see that the codomain of f is the domain of g, right? Basically these two sets are actually the same sets, meaning that this set is actually the same as this set, right? So that is one important thing here, and another important thing is that basically this function up here is bijective, meaning that it is invertible, and this function over here was also bijective. Meaning that it is invertible. And so based on these two functions, we showed that g of f whole inverse was f inverse composed with g inverse. Now, based on that, we are saying that let f be a function from x to y and g be a function from y to z, meaning that y and y are basically the same sets here. And let these two be two invertible functions. Invertible functions. So if these two are two invertible functions, what that means is that f is basically a bijective function. It's 1, 1 and onto, and g is also a bijective function, meaning that it is 1, 1 and onto, and so based on that they are both invertible, right? Then g of f is also invertible, and of course we showed that in the same in the same example, we showed that GOF was also invertible, and we did also find the inverse of GOF as well. So then you can say that GOF is also invertible, with basically GOF whole inverse. GOF whole inverse is the same thing as F inverse composed with G inverse. That is basically theorem number 2. And in order to prove this theorem, basically to show that GOF is invertible, so the proof for this theorem would be basically in order to show that GOF is invertible with basically GOF is invertible with GOF whole inverse is the same thing as F inverse basically composed with G inverse. It is enough to show that so you want to show that GOF is invertible, right? So we said that basically previously what we said that basically if we had some function f from a to b, and suppose that there is some other function g which is supposed to be the inverse of f, and that goes from b to a, in order to show that g is the inverse of f, we need to show that GOF is the identity function on the domain of f, and FOG is the identity function on the codomain of f, which is I of b, right? So now we need to do the same thing over here, meaning that we want to show that GOF is invertible. So I can basically I'm going to assume that the inverse of GOF is GOF inverse. So basically following the same logic over here, you have to write the inverse first, as you can see here. So the inverse is GOF whole inverse, and you want to compose it with the original function, which is GOF, and that is supposed to be the identity on the domain of the original function. The domain of the original function is basically, you know, that GOF goes from x to z, right? So the domain is x, so that becomes I of x. And you also need to show that basically the other way around, meaning that instead of GOF inverse composed with GOF, you write GOF composed with GOF inverse is equal to the identity function on the codomain of GOF. The codomain of GOF goes from x to z, so the codomain becomes z, I of z, right? Now, what you need to do is that just simply show these two, and then you will have shown that basically GOF is invertible, right? So now that in order to do that, you can say that F inverse composed with G inverse, F inverse composed with G inverse, composed with GOF, you can say that I of X, I of Z. So now if I write basically, okay, so let me see. Okay, so now basically what seems to be the case here is that, well, of course, here we are saying that then GOF is also invertible with GOF whole inverse is equal to F inverse composed with G inverse. Now this result over here, as far as I know, we have never proved it. But then they have actually used it in this proof over here. Okay, so that's I assume they have taken it as a theorem, some theorem that we have proved, and so they have used it in this proof here. And so since they have done that, I have to do the same thing, meaning that I'm going to assume that we have proved this and that we can use it in this proof over here. So then if that is the case, and if I am allowed to use this in this proof, what I'm going to do is that I'm going to rewrite this as basically GOF whole inverse. I'm going to write it as F inverse composed with G inverse, meaning that I'm going to write this as F inverse composed with G inverse, and then compose that with GOF, and I want to show that that is equal to I of X. And also I'm going to use the same thing over here, meaning that I'm going to write GOF and compose it with GOF whole inverse, which is the same thing as F inverse composed with G inverse, based on this result over here. And I want to show that that is equal to I of Z. So I call this number 1, and I call this number 2. So now basically the way that we can prove this, number 1, you can argue that basically F inverse composed with G inverse whole composed with GOF is the same thing as well, basically in theorem number 1 we said that if you have these three functions in which basically you can see that the codomain over here is the domain here, again the codomain here is the domain here, and these three functions are three functions, just three functions, then you can say that H composed with GOF is the same thing as HOG composed with F. Meaning that I can write this as, I can take this as one single function. I can take this as one single function and write it as F inverse composed with G inverse, and then compose it with the first function over here, compose that with G, and then compose the whole thing with F. Right, so that I can do. This is by theorem number 1. Now, again, using the theorem number 1, I have F inverse composed with G inverse, and the whole thing has been composed with G. So then I can write that as F inverse composed with basically G inverse composed with G, and then I can write that as composed with F, right? Composed with F. This is again using theorem number 1. Now, over here what we have is G inverse composed with G. Now, you need to, there is something here to understand. Basically, when you say that, basically what we are saying here is that F is some function here, G is some function here. These are two functions, right? So these are two functions. So you have F inverse, G inverse, and F, and so on and so forth. And these are invertible functions. So I am going to basically create two functions here in order to show you something about this G inverse and G, and what is the composition of these two functions. So if you have some function F, for example, let's say that I wrote this somewhere over there. Let's say that, for example, you have some function G, for example. Let's say that your G is, you have some function G which goes from some set, for example, X to some set Y. And I'm going to say that, and of course you know that G is invertible. G is invertible. Meaning that let's suppose that, for example, X is equal to some set, for example, ABC, and Y is equal to some other set, for example, 1, 2, 3. And then, for example, the rule of this function is, for example, G of A is equal to 1, and G of B, for example, is equal to 2, and G of C is equal to 3, for example. As you can see, the function is 1, 1. It's also onto, so it's a bijective function, so it's invertible. And so then based on this function, I can create another function G inverse, for example, and I can say that basically this function G inverse goes from Y to X, and then the rule of the function, the same X and Y, of course, and then the rule of the function becomes, for example, G inverse of, for example, 1 is equal to A, and G inverse of, for example, 2 is equal to B, and G inverse of, for example, 3 is equal to C. G inverse of 3 is equal to C, right? So now let's see what we can show using these two functions here. Actually, this is just the inverse of this function, right? So here basically what I want to calculate is G inverse composed with G. G inverse composed with G. Let's see what that is. So G inverse composed with G, what that's going to give you is that the argument of the function G can be basically A, B, or C, because the domain is X. So I write it as, for example, G inverse composed with G of, for example, A. And that's the same thing as G inverse of basically G of A, and G of A is equal to 1. It's equal to G inverse of 1. And that is equal to G inverse of 1 is equal to A. So as you can see, G inverse composed with G of A is equal to A. By the same logic, G inverse composed with G of B is equal to G inverse of basically G of B, which is equal to G inverse of G of B is equal to 2, and G inverse of 2 is equal to B. And again, you can see that G inverse composed with G of, for example, C is equal to G inverse of G of C is equal to basically g of c is equal to 3, so that's g inverse of 3. G inverse of 3 is equal to c, which means that G inverse composed with G is the, meaning that based on this 3 you can say that G inverse composed with G is equal to the identity function on the set X here, which is basically the domain of G here, right? That is I of X. That is the domain, the identity function on the domain of the original function, not the inverse function, but the original function. So then based on that, I can say that G inverse composed with G is equal to the identity function on the domain of this function G. The domain of this function G, here we argued that is Y, right? So that becomes I of Y. And so you have basically F inverse composed with I of Y, and then compose that with F. That is basically what you get here. Now, let's say that you have some function F, and you have some function F inverse, and you have some function Y. So let's say let's take an example here and take a look at some example functions here. Let's say that you have, let's create some function F, the inverse of that function, and some function Y, for example. Let's say that you have, for example, this set A here, and then you have a set B here, and then you have a set C here, and basically and of course Y is just a set here, right? Y is just a set here. Okay, so let me see. Y is basically only a set here, which is the codomain of F, right? Y is the codomain of F. So I'm going to create simply only one function. So this is not a good example. So I'm going to create one simple function F, for example, from some set X to some set Y. And what I'm going to do is that I'm going to create the same situation here, meaning that theorem 2, I'm going to create basically this function, and I want to make it invertible, right? I want to make it invertible. So let's suppose that F is invertible. Let's suppose that F is invertible, meaning that I create some set X over here as, for example, 1, 2, and 3. And I'm going to create some set Y over here as A, B, C. And I'm going to say that, for example, F of 1 is equal to A, F of 2 is equal to B, and F of 3 is equal to C. And so based on this, you can say that if I create the inverse of this function, F inverse that goes from Y to, F inverse that goes from Y to X, then that function, the same X and Y, then you can say that then F inverse of, for example, F inverse of A is equal to 1, and F inverse of B is equal to 2, and F inverse of C is equal to 3. So that is basically the situation that we have here. Now we want to evaluate this expression, f inverse composed with I of y, f inverse composed with I of y, composed with f. So what we want to know what that is. So in order to evaluate this, so of course you know that the arguments of the function f are basically the members of the set x, which is 1, 2, and 3. So let's make the argument one of the members of the set x. For example, let's make it a 1. So this is the same thing as f inverse composed with I of y, f inverse composed with I of y of basically f of 1. Now f of 1 over here, as you can see, is equal to a. Is equal to f inverse composed with I of y of a. Now I of y is basically this the identity function on set y. Okay, so continuing with this problem, so you can write this as basically f inverse of basically I of y of a, right? Now I of y is the identity function on y, and the only thing that it can accept is only the members of the set y. Now the members of the set y are a, b, and c, and you know that basically I of y, what it does, whichever members of the set y you input into this function, it's going to give you the same thing back, meaning that if you give it a, it will give you back an a. If you give it a b, it will give you back a b. If you give it a c, it will give you a c, but you cannot enter anything else into this function, because it accepts only the members of the set y, because it's the identity function on set y. You might be able to basically enter other things into this function as well, but as far as, I mean, for all we know, we just don't know what the output is going to be. So the only thing that we know is that basically if you input any of the members of the set y into this function, you're going to get the same thing back, which means that if I input a into I of y, I'm going to get the same thing back as a. So that means that is going to be f inverse of a, and f inverse of a is equal to 1, right? So as you can see, this expression here, the whole thing, f inverse composed with I of y composed with f of 1, is giving me 1. Now I can try another one of these, meaning that I can write f inverse composed with I of y composed with f, and as another argument I can give it a 2, right? So that would be the same thing as f inverse composed with I of y of f of 2. That would be f inverse composed with I of y of basically f of 2. Now f of 2 is basically equal to b, right? F of 2 is equal to b, so I can write f inverse f inverse composed with I of y, and f of 2 is equal to b. So I can write this as basically f inverse of I of y of b, of I of y of b, right? Now, and then I of y of b, as we argued before, basically I of y of b is going to give you b back, meaning that this is equal to f inverse of basically b, and f inverse of b is equal to 2, meaning that this function, or this whole function over here, which is basically, and if you if you enter a 3 over here, meaning that if you write f inverse composed with I of y composed with f, and if you give it an input 3, it's going to give you a 3. So basically here we input, here basically what we did was that we input a 1, we got back a 1. We input a 2, we got back a 2. We input a 3, we got back a 3. That means that basically f inverse composed with I of y whole composed with f seems to be the identity function on the set that contains these elements 1, 2, and 3. And 1, 2, and 3 is basically simply x, right? So that is I of x. So which means that I can write this as I of x, right? So, and that is the result that we wanted to show. We wanted to show that f inverse composed with g inverse composed with g of is equal to I of x, and that's basically what we got. And using the same logic, then you can show that g of composed with f inverse composed with g inverse is equal to I of z, and that proves that basically g of is invertible with basically this. And what we wanted to prove here was theorem number 2, that basically you have these three functions f, g, and f and g, these two functions, x to y, y to z. The codomain here is the codomain here is the domain here. The codomain here is the domain here, and both of them are invertible. Then g of is also invertible. So we showed that g of is also invertible. And in order to show that g of is invertible, we had to show basically all of these two results. We showed one of them, and using the same logic you can show this one as well. And that proves that basically if you have two functions f and g in such a way that the codomain of the first function is the domain of the second function, and if both of them are invertible, then g of is also invertible, meaning that if you happen to be a visual person, then you have this x, y, and z. You have the set x here, you have the set y here, you have the set z here, and there is a function f that goes from x to y. There is a function f that goes from x to y. There is another function that goes, there is a function g that goes from y to z. There is another function g that goes from y to z, and f and g are both invertible. Right? Now, based on these two functions, since both of them are invertible, you can find another function GOF, which goes from basically x to z, GOF, and if these two are invertible, then GOF is also invertible. That is basically the whole story here. Okay, so that was basically theorem number 2. Now we have another question here that I think we can solve this problem as well, and then end this video, because this is the end of this section. So okay, so the last example that we have here is example 28. Example 28, which is basically let S be equal to a set which is basically 1, 2, and 3, and determine whether the function, so we want to determine, oops, we don't have much space, determine whether the function basically f from S to S defined as below have inverses. Defined as below have inverses. And find f inverse if it exists. I want to find f inverse if it exists. Okay, so in the first case here is basically A, which is basically S is a set 1, 2, 3. F is a function from S to S, and basically you want to know if F has an inverse, if F is defined as, for example, this set as 1, 1 and 2, 2 and 3, 3 and 3, 3, right? So 1 to 1, 2 to 2, 3 to 3, which means that F is basically injective, and surjective, or you can say basically it is basically 1, 1 and onto. So since it is 1, 1 and onto, then of course the inverse of this function exists, and you can say that f inverse would be equal to basically all of these ordered pairs just swapped around, meaning that instead of 1, 1 you would get again the same thing 1, 1, but basically that would be the inverse function, although it looks like it's the same thing. 1, 1, again 2, 2 and 3, 3. That is the f inverse, meaning that, for example, if you have some function like, for example, f of x is equal to x, then again f inverse of x would be the same thing. F inverse of x is equal to x, because if you have a 45 degree line, if the line makes a 45-degree angle with the x-axis, then again the inverse of the function is again the same line. So that's basically what happens. And the second case that we have here is case B, and that is basically f is equal to 1, 2, and then it's equal to 2, 1, 2, 1, and then you have 3, 1. 3, 1. So as you can see, 1, 2, and 3 are both if f is supposed to be a function, since f goes from s to s, so you have 1, 2, and 3, and 1, 2, and 3 as the domain and the codomain of the function, and f goes from s to s, right? Now here we have 1 to 2. Here we have 1 to 2, and then 2 to 1, and then 2 to 1, and 3 to 1. So 3 to 1. And so as you can see, the function is not 1, 1. Since it is not 1, 1, there is no inverse. It cannot have any inverse. Because then basically when you want to get back from get back from 1 to the domain of the function, the inverse of the function, basically the function itself goes from here to here, that is f. But then f inverse goes the other way around. That would be, for example, f inverse. That would be f inverse. Now f inverse has to map, basically if f, for example, maps 2 to 1, then f inverse has to map 1 to 2, 1 back to 2. Now the problem over here is that basically then in the inverse function, 1 would be mapped to 1, 1 would be mapped to 2 and to 3 as well simultaneously. And that results in the fact that, that basically creates the problem that the inverse will not be a function in the first place. So the inverse in this case does not exist. So that is basically this one. Now, so here you have no inverse. Now in the third case that we have here, case C, we have f is equal to basically the set 1, 3 and 3, 2 and basically 2, 1. Right? So 1, 3, 3, 1, 3, 2. Okay, so this is 1, 1 and basically onto, meaning that you have all the first numbers in the ordered pairs are the elements of your domain, and all the second numbers are the elements of your codomain, meaning that you can write over here 1, 2, and 3, and this is S, which is your domain. And then you have 1, 2, and 3, and basically this 3 over here, this 2 over here, and this 1 over here are these 1, 2, and 3 over here. So this is your codomain. Now this is again S, right? And these elements 1, 3, and 2 are these elements here, 1, 2, and 3. So the first elements are your domain, the second elements are always your codomain. Now you can see that 1 is mapped to 3, and 3 is mapped to 2, and 2 is mapped to 1. So as you can see, the function is 1, 1, and it is onto. And therefore the inverse exists, and the inverse is actually f inverse is equal to basically the inverse of these, meaning that 1, 3 becomes 3, 1, 3, 2 becomes 2, 3, and 2, 1 becomes 1, 2. Right? So that is basically an overview of these examples In the next video, we will talk a little bit about exercise 1.3. So I'll see you in the next video, and thank you.